So today we'll talk about trusted computing. We're going to cover a couple of interesting, diverse aspects of trusted computing and confidential computing, trying to focus on some of the properties that are going to be provided by trusted computing, and then dive into mechanisms that allow enforcing of trusted computing. So some of the learning goals today are the needs of trusted computing, different ways of, whose is it? Different ways of use cases that can be looked at, different kind of guarantees provided by trusted computing, like how can we leverage trusted computing to give higher level guarantees on top of software or other aspects. Maybe even if a couple of untrusted layers are in between in the form of confidential computing. Different kind of threat models, and we're going to discuss varying threat models, and just also so that you have a bit of a highlight of different key technologies, different ways how to implement it, and so on. And we're going to end with a discussion of side channel attacks and different levels of side channel attacks that are often used to break trusted computing. So join me for this discussion. As always, feel free to ask questions. It's going to be fun. Now, one aspect that we've already covered extensively in the class is if you can trust applications. And if you've paid any attention at all, you would answer this question with a very clear no, right? Because there's always going to be bugs in applications. There's going to be so many abstractions across all the different layers of the system that it's going to be next to impossible to protect and secure all of these layers. Software systems like operating systems, hypervisors, compilers, runtime, static libraries, the application itself, and a ton of other applications are extremely complex. There's hundreds of millions of lines of code maintained by a large amount of different people that frequently have bugs, right? Even though the bugs, as soon as they are discovered, at least the vulnerabilities, as soon as they are discovered, will be fixed, hopefully, after some time, maybe once a month, maybe once every 3 months, every 6 months, depending on your update policy. But there's a countless source of new bugs and new vulnerabilities that we'll always have to fix. So we can't trust applications because of their massive amount of complexities. But what about hardware? Right? We are facing a similar dilemma when we're looking at hardware. The computer could be owned or controlled by another entity. So for example, if you're running some kind of computation in the cloud, you're trusting the cloud provider to actually make sure that the application that you want to run is run. But also, the hardware is extremely complex and was built by different set of untrusted parties. Right? So you don't have any insight into the specification of whatever Intel, ARM, Apple, or so on is creating. Right? You don't know the programs that they are running. There may be even hidden secret CPUs on your main CPU that are computing something very, very different. And you don't even know what the fab is doing, such as TSMC, that are actually fabbing the different architectural designs that were created by Intel or ARM or Apple or whoever, right? So you've got several layers of closed source enterprises that are trying to implement their things, and you have to trust them to some extent. But you can't really trust the underlying hardware itself. Now, assuming that we don't have trust in hardware, how can we make sure that we can somehow trust what the computer is doing, right? Is there a way for us to get us some notion of trust, some foundation of trust to allow us to infer, at least for some computation, that stuff is going all right? So maybe if you rephrase the question a bit, can we trust the hardware or some aspects of the hardware? We can as soon as we have trusted hardware. And to get trusted hardware, we need to have a couple of primitives. So according to the Trusted Computing Group, a piece of hardware can be trusted if it always behaves in the expected manner for the intended purpose. Meaning that we have a clear set of definitions, a clear specification of how the hardware should behave, and we have a guarantee that it will not behave otherwise, according to the threat model, right? Now, imagine that, like, instead of having to trust the whole system, the whole ecosystem, the whole stack of software, you only want to trust a little piece of software. So imagine you could build a very small version of your program that you trust, like you even formally verify it or whatnot, and then executes the program perfectly. You put this mini program in a computer to execute your programs, and then you ensure that no other outside party can actually look inside or extract the secrets from this super locked-in safe. And this is pretty much what trusted hardware actually provides and gives you. So if you look at the key properties, there's 3 key properties that are being provided by trusted hardware, namely attestation, isolation, and sealing. And together, they allow us to execute certain programs, certain code, certain applications in a secure manner, even if we don't trust the full stack. Right? So attestation is a mechanism that allows us to prove that hardware does what it's supposed to do. So attestation tells us that, hey, this hardware is the hardware that I actually expect. This hardware is actually running the program, the mini-me that I ran or pushed into this secure compartment. Isolation is another key property that tells me that the privileged code that is being executed on the hardware cannot be observed. Like, we cannot observe the computation that my secret program is doing or extract the data from this like isolated component. So isolation gives me a guarantee that whatever happens inside this isolated box cannot be observed from the outside. Sealing finally allows me to take whatever is in this safe and dump it somewhere else. So for example, we take it from the cache that is somewhere in the CPU and can dump it on the hard drive or on the SSD without an attacker being able to recover the internal state of the hardware that we looked at. Right? So these are the 3 key properties that together allow us to enforce trusted confidential computing on trusted hardware. Attestation, isolation, and sealing. And let's now spend a minute or 2 on each of these properties to go a little bit deeper. Attestation proves that the system is in a specific state to an authorized party. Right? So essentially, this is a trusted hash over all the internal state of your safe. Now imagine you're running a process or you're running a program or whatnot. Attestation gives you, like if you start the attestation program, you get a hash that tells you that, hey, all the code, all the data, all the details of my program are this. And you kind of map this to a, I don't know, SHA-256, SHA-512 hash that you can then verify. And if the hash is what you expect it to be, you know that this is actually the value that you expect it to be. So let's say the prover is running the secure hardware on the side, right? And you measure the state of the system by using the nonce and then appending all the data to it, piping it through a SHA hash, and then sending H back to the verifier, and the verifier can check if the hash actually matches whatever it expects, because the verifier knows, for example, this is the state that I expect, this is the nonce that I use, therefore I can concatenate as well and actually get to the same expected value. Right? So attestation allows you to ensure that, hey, this is actually the state that I assumed. Now, we require some trusted hardware for that to do the actual measurement and the hashing. Right? So we assume that we have some magic hardware that does the measurement of the state and then sends it back through some form of channel. Question? Yes, please. The nonce is being used as part of the measure. So the very first data piece is used to set up the stage, and then the rest of the data is being appended. Why do we need a nonce? As a follow-up. And anybody can answer if you want. Go ahead if you know. Replay attacks, exactly, right? Otherwise, we would only need to know the hash once as an attacker. We would only have to observe the hash once, and the nonce protects us against different kinds of replay attacks. Correct? So yeah, attestation allows us to kind of map the state, the internal state of our safe into a single value that can then be checked afterwards. Isolation enforces that whatever is happening inside our computational box cannot be accessed from outside. So it gives us some form of access control, right? So let's say our secure app is running there, and we get guarantees that neither the operating system nor the hypervisor can actually access the data of the secure app. The operating system or hypervisor, depending on the execution model, may stop the app. Right? So it may interrupt the app and pause the app and rerun it later for scheduling purposes. But the operating system, it may even give the secure app additional pages of memory or remove pages of memory. But the operating system cannot look at the content of the internal state. Right? And we'll discuss this in the SGX execution model a bit later on. So unauthorized applications cannot access or write to the region of memory that the secure app uses. And trusted hardware offers one well-defined entry point to interact with the software. And we need this one single well-defined entry point in the software, as otherwise an attacker could jump into random arbitrary places in the application, which could then, for example, leak secrets. Let's say your secure app does a check, if password equals whatever, then return the secret key, right? Now, if the attacker knows that this is the app that you're running without a well-defined entry point that would carry out the access check, the attacker could just jump to the instructions right after the check, right after the password check, and leak all the information to execute this functionality. This is why we need well-defined entry points to enforce control flow integrity inside the application. Otherwise, the attacker could jump to arbitrary locations, thereby breaking the isolation and leaking internal state of the application. And again, as before, we've got this TCB, or trusted computing base, which we actually rely on for the additional guarantees. This could be either in software or in hardware. As we've seen on ARM, in the mobile class, EL3, that's a secure monitor, is actually a piece of software that interacts between the normal world and the secure world where all the trusted applications are. So on ARM, the interaction between the two parts is implemented in software. Whereas on x86 for SGX, we have a fairly large TCP in the hardware where we implement entry gates and so on at the hardware level through the SGX protocol. Sealing protects private information by binding it to a platform configuration or the state. So essentially what we do is we seal data according to a state, we get a hash, and to unseal, we need to provide the same state and the hash. Right? So the state X may be the state of the module, configuration information, including the different software, hardware, or whatever you use. This allows us to store some of the state in persistent memory and untrusted persistent memory. So this allows a system, like a trusted computing system, to dump information on the disk, for example. And the trusted hardware would only allow loading the information from disk again, correctly decrypting it if the state matches. As in, the correct software is being loaded, the correct keys are being loaded, the correct configuration is loaded, and only then can the information correctly be recovered from the disk. So far, so good. So we know attestation, we know isolation, we know sealing. Let's now look at how these concepts can actually be implemented by actual hardware. So trusted hardware comes in many different forms and flavors. And any hardware that has been certified to perform according to this set of requirements under strong adversarial conditions can be called trusted hardware. And the three types of trusted hardware that you're most likely interacting with is a TPM chip, for example, potentially a hardware security module, and Intel SGX. Any ideas where TPM chips are? Yeah? Yeah, so this could be in your laptop or in your desktop. Where else? You could be using this on a server to verify a given state or whatnot. Where would you use a hardware security module, an HSM? Any ideas? This is often used in cloud environments to store cryptographic keys of large amounts of users because it provides tamper-resistant hardware. We're going to cover this in a couple of slides later on. Intel SGX. What's the main use case for Intel SGX? Who has heard of Intel SGX? The software guard extensions. 2? More? Like, raise your hand if you've heard of Intel SGX. 1, 2, 3. That's not 4. That's not too many. Okay. Yeah. Have you heard of a use case? No? In academia, it's mostly used to demonstrate the effectiveness of a side channel if you're trying to publish a paper. So you're using SGX to show that it is broken, and then you get your paper accepted. So it's one of the use cases. It's a very sad use case, but it's one of the use cases. Other use cases are on the server side. If you don't trust the cloud provider, that's the business model, right? You don't need to trust Amazon, but you can run it in a secure enclave. So you can provide it's providing this mini-me trusted box to kind of offload some computation there. And it was used on client side, right? It's being deprecated on the client side, but do you have any idea what it could have been used for on the client? Like, why would it be used on your end? DRM, yes. What kind of DRM? Why would it be useful for DRM? Do you know what DRM is? Say again? So you cannot record a video, for example. Yeah. DRM, like essentially, it's called digital rights management, and it ensures that, for example, if you're streaming a movie, that you cannot steal the movie, or at least that the movie the movie that was stolen and later shared can be traced back to you. So how could you do that, right? So DRM on one end would be like decrypting a stream of like an encrypted HD stream of a encrypted video stream, and then displaying it on your monitor. Even potentially with end-to-end encryption between your CPU and your monitor to ensure that you cannot like get the signal anywhere in between. Now, SGX was used for example, playing Blu-ray videos, Blu-ray discs, and Netflix, 4K streams and whatnot, to make sure that the stream doesn't leak. Now what they did is, ideally, right, each stream would embed a secret watermark of the user ID. But for that, you need to re-encode the video to some extent. And this is obviously expensive. And Netflix obviously doesn't want, or whatever DRM company obviously doesn't want to pay for this high server cost, right? If you stream the video stream without watermark to the client can steal it before the watermark is being embedded, right? So you obviously want to have the watermark in the video stream before it is actually sent to the client. Now, but you don't want to pay for the computational cost of actually adding the watermark in the cloud, because it's expensive. So what you do is you have this secure enclave, this trusted computing enclave on the client, where you send the encrypted stream in, the enclave decrypts the stream, adds the watermark, and then sends it outside. And that way you can use the computational capabilities on the client to decrypt the stream and add a watermark or do something else on top of it. Now, it's being deprecated on the client side because of side channels and different kind of attack vectors, but this was one of the main uses that SGX actually has. Now, the different types of trusted hardware answers to how trusted computing can be achieved, right? So it provides mechanisms. TPM provides a certain set of mechanisms. An HSM, hardware security module, provides a certain set of mechanisms. Intel SGX provides a certain set of mechanisms. And we're going to start with TPM chips and then walk through the different options. The TPM chip, or a trusted platform module, is like a small piece of hardware that is embedded in a complex hardware design. And what it allows is essentially it allows kind of attestation of state of the system. For example, currently all the memory pages that are being mapped, or currently the memory region between address X and Y is this state. The registers are this state, right? So the TPM is a special chip that you can invoke to say, now please give me an attestation of the current state, and then it provides you with an attestation of the current state. So it has an attestation key, a storage root key, and a password that is being set. And using these two keys, it can actually sign in a cryptographically secure way the current state of the system, or it can dump certain bit of information using sealing. So it's a separate chip that can securely store artifacts such as keys or passwords and do cryptographic operations. It doesn't store data, right? So it doesn't store it doesn't store megabytes of data. Usually a TPM chip has 16 slots of 160 bit, for example. Right? So it's very small storage area, but we're only using the storage area for cryptographic keys. Right? So this allows us to securely store a set of keys. The hardware itself is tamper resistant. As soon as you're trying to fudge with the TPM chip, it will destroy itself and prohibit any further modification. So if you're doing attestation, right, through a TPM chip, we can do this through so-called PCR registers, or platform configuration registers. Whenever we power on the system, these PCRs are initialized to 0, like a default value, and then you can only append during the execution. Right? As long as you're executing, you can append. So you cannot reset them, you cannot write to them directly. So the only operation you can do is you can do a TPM extend based on a parameter D, such as the current data region, like the current register values or the current state of the CPU, the register file, plus whatever data you're looking at. And then you can call tpm extend d, which is whatever data region you're looking at, and then you calculate the new hash that is being stored in the PCR that you give. So PCR n, the nth register between 0, 1, 2, 3, 4, 5 or whatnot, is SHA-256 of the existing state of the PCR n plus appended whatever state there is, right? So this gives you a way to add the state of your system at certain intervals, and then compare against these intervals. So each measurement is being added, and then you can check for this measurement. So let me walk you through an example, and some of you may have heard of Secure Boot. And Secure Boot is actually using TPM as an example, right? So in Secure Boot ensures that all the different stages of the boot process are verified and checked, and that malware cannot install itself somewhere in this boot process. Otherwise, Secure Boot would fail. And when we are booting a system, when we are booting a laptop, we go through several stages, from the BIOS to the bootloader, first stage bootloader, second stage bootloader, kernel, yada, yada, yada. And we add more and more stages, and we go through the initialization of a lot of complex system. And each time, we're going to check and verify. So when we power on a computer, the very first thing that happens is it reads the BIOS boot block, starts executing that. At the end of the BIOS boot block loads the BIOS. Right? So the BIOS boot block finishes executing, and it bootstraps, right? It goes to the next stage, it reads the BIOS. Right? So if you think about it, when you turn on a computer, like, it doesn't magically just start executing Linux or Windows. It needs to go through several stages of initializing all the hardware. The very first time you power it on, it executes a couple of instructions that are hard-coded in a BIOS boot block. And these instructions are, let's go to the flash chip that contains the BIOS. Load the BIOS step by step into memory, and then start executing the BIOS. So the BIOS boot block loads the BIOS, measures the BIOS, right? Is this actually what I expected? And then asks the TPM to extend the value. Okay, so we've now updated the PCR, and the BIOS then initializes the hardware, and the OS loader, the operating system, like this could be grub, this could be the Windows loader, this could be any other kind of operating system loader, and the BIOS again extends the PCR by whatever data it has loaded from the hardware and the operating system. After the OS loader, we load the operating system kernel into memory. We start measuring it, extend the TPM, and later on we actually start loading the applications, and we can check and ensure that the current values, the current PCR values, are what we expect. At any point in time, we can send and validate that, hey, before we actually branch to this other piece, we make sure that this is what we expected. If it is not what we expected, then we can terminate the system, say Secure Boot has failed, we are not in the expected stage. So for example, somewhere on the, somebody has modified the bootloader on the hardware or whatnot, and we don't trust it. So far, so good. Now, this covers attestation. Now, let's talk about sealing as well. Since a couple of years, most systems are using full disk encryption, and sealing is a perfect example of, like full disk encryption is a perfect example of where we can use sealing. And sealing is we can We can leverage an owner password to store a cryptographic key on trusted hardware. So even if the hard drive would get compromised, the key is only stored in this TPM and would allow us to protect the data on the hard drive. We don't trust the hard drive itself, right? We don't trust any part of it. And we need to store the cryptographic key somewhere. The TPM is one place where we can store this information, right? So the TPM would allow us to map from an owner password to the actual key, so that, for example, BitLocker would protect access to the hard drive and only allow decrypting it whenever the correct password was entered. Right? So this is an example where we use trusted hardware to store this. Another example would be that we create a cryptographic key from the password itself and store it in untrusted memory. But this often has much lower entropy than what the TPM provides. Right? If you think about it, the TPM allows us to map from a password to a cryptographic key in a secure way, but we trust the underlying hardware. If we don't trust the underlying hardware, we could create a password that is long enough to initialize the cryptographic key, but this would be prone to brute force attacks. Like if you only have a PIN, for example, this would not be sufficient. And the TPM can count how many times you try to enter the password, and then, depending on the configuration, destroys itself if you did not enter the correct password for like 10 times in a row or something. Hardware security modules is the next piece of hardware. They do have a TPM chip inside to guarantee certain properties, and they run a very particular piece of software that is bootstrapped through this secure boot process into the system. So hardware secure module is pretty much a computer with a TPM chip that runs dedicated software. So these are very customized devices that are used to store secrets. For example, large amounts of cryptographic keys, large amount of private data, and the goal is that they destroy themselves whenever they are tampered with. So when you're trying to open the box, the system would flush all kind of data, destroying itself in the process. So think of it as a tamper-resistant hardware device that is using a TPM chip inside to protect itself against different kind of modifications and different kind of changes. The HSM, like the API to access an HSM, is specified in a protocol that allows the common interactions for different kind of cryptographic operations. Smart cards follow the same protocol, and it kind of gives us a set of rules and ways to interact with these systems through this PKCS11 API. There's applications, tokens, slots, and whatnot. Slots are logical access points to the cryptographic device, slot 0, 1, 2, 3, 4, 5, and gives us a way to enumerate different parts. Tokens are a logical view of the underlying cryptographic device, so one token per HSM, mapping the different functionalities it supports. But then the session, right, as soon as you have an application interacting with the underlying slots of the HSM, gives you a logical connection between an application and a token. This is a way where you run software that is then interacting with this view of a TPM to some extent. This is somewhat complex at a technical level. It's a complex API. Let me walk through a simple example. An application authenticates itself to the HSM and creates a secure session, right? So the app is outside, initializes itself, creates a secure session to interact with one of the slots on a token. The app key asks the hardware secure module to generate an AES key, the HSM returns the AES key through the session, which is encrypted. Crypto data to be the HSM then sends back the encrypted. The application sends the data to be encrypted to the HSM, and the HSM goes through the crypto engine, sends back the encrypted data over this channel, and then the application closes the communication session. This is a very complicated way to interact. Also, it's often quite slow because you need to go through dedicated hardware, you need to open up a channel, you need to open up the connection, and this requires quite a bit of additional resources. So this works rather well in high secure environments if you have low throughput data, but it comes at a fairly high cost of this dedicated hardware that is tamper resistant, that is expensive, and that is guarded against malicious access. And Intel thought, oh, these HSM companies are making way too much money. Let us step into this game, and let's add this extension on top of Intel x86, where we can enforce a trusted enclave. So the idea here was that at the hardware level, Intel implemented a set of extensions that allowed the creation of trusted enclaves that are protected from a malicious operating system or hypervisor, where the SGX engine ensures that the memory of the enclave is encrypted, the data of the enclave is encrypted. There's no leakage across enclaves or across the enclave and other parts of the system, and thereby isolating the different components from each other, plus providing attestation capabilities using a special trusted enclave, the attestation enclave, and then offering sealing capabilities to dump the state as well. The operating system remains under control of scheduling, when to run an individual enclave, when to stop it, page allocation for individual enclaves, like how much memory an enclave actually gets, and like all other operating system primitives. The enclave itself cannot do any system calls, but it needs to go through an untrusted user space component and the operating system to do system calls. But the computation that is happening inside the enclave is protected from any prying eyes. Let's walk through an example. Right, we've got the operating system, the hypervisor, and the application, which is untrusted. You execute a special instruction to create an enclave. This is in user space. And then the CPU will create an enclave, which has a start and a return, code to start and return, and a call gate through which the operating system or any other component can enter the enclave. So again, here we've got this dedicated entry point into the enclave, which is one single entry point, right? The application can then call the enclave, which goes through the call gate to then start and maybe return some information. Whatever is happening inside the enclave cannot be observed. Only whatever the enclave decides to copy outside, for example, moving data back to the untrusted part, to the rest of the memory, can be observed by returning this information. The operating system itself cannot call into the enclave. You need to go through the application, but thereby protecting against different kind of accesses. The operating system can neither call the call gate nor into the enclave itself, nor observe the memory of the enclave. Right? So the enclave is isolated from the operating system and all the other remaining processes on the system, thereby protecting it against adversarial access. SGX allows attestation. Two types of attestation: local attestation and remote attestation. So local attestation is you can observe on the same machine if data is correct or not, or remotely. Right? On the local machine, one enclave can attestate another enclave. For example, check the integrity of the other enclave by using report. So here, for example, enclave 2 can measure the enclave 1 by calling measure enclave. Enclave 1 then says, sure, I would be happy to do so. I create a report inside the enclave. It creates a report by calling eReport. This is one of the internal functions. Returns it. Enclave 2 can verify the report if the report is actually what it expected it to be, and then return the value or the information. Right? Remote attestation, on the other hand, uses quote and report to then forward it to the other side. So for remote attestation, you can use this local attestation is then being forwarded through a TLS channel. Intel provides an attestation enclave that you can use on different systems to then ensure that, hey, this is actually the enclave that I expected to look at. Right? So it's like a way to bootstrap remote attestation through local attestation. Cool? So let's see what this can be used for, especially in the context of SGX. And we'll look through a particular use case, namely Signal. Who's using Signal for communication? Who's not using Signal for communication? Out of those not using, who knew about Signal before? Okay, why are you not using Signal? Out of interest, just go ahead. In my bubble, everybody's using Signal. I don't know what you... All of my friends are using Signal. I don't know what's up. Other reasons? Yes. Speak up. Synchronization between devices. What do you mean? Yeah. Like you cannot easily run Signal on like the crappy, shitty Electron app on like 10 different devices. That's true, but it's also true for WhatsApp, right? It's not super easy to run it on many different targets. It's synchronized. Okay. Who's running WhatsApp? Everybody. What other communication platforms? Telegram? What else do we have? Messenger? The last three. I don't know, Discord? Most others. What am I missing? I don't know. Any that I missed? Matrix, yeah, Element, true. 1, 2. Who's running Matrix? 3, yeah. So Signal is a messaging application that should offer or is aimed to offer strong privacy protection. It uses end-to-end encryption, and it pioneered end-to-end encryption. So the Signal protocol has then been taken over by WhatsApp to actually provide end-to-end encryption, and also Matrix to provide more complex group communication. The keys are stored on the device. It's mostly open source. Well, there's some caveats there. And it's an independent, not-for-profit organization. And we actually had Meredith Whittaker from the Whisper Foundation as a keynote speaker when I organized NDSS. It was a super fun event to hear her talk about some of the challenges that they are facing when they are implementing such a secure communication platform. Highly recommended to watch the recording of the talk. Now, but Signal as a communication platform is not the reason why I'm bringing this up here. The reason why I'm bringing this up here is that like to use a communication platform, you need to know who of your friends are also using this communication platform, right? And for that, you need some form of contact discovery. And here the idea is, you know that you have your address book, but you would like to figure out who of your friends is also using Signal. And hopefully it's a lot of them, right? So what you need is the intersection between the people using Signal and all your contacts. Now, you need the full set of Signal users, and you need the full set of your address book. In this threat model, like whom do you want to protect against, why, and what data is actually needed?
Maybe we don't want also to get the list of people who are using Signal from Signal server.
Yeah, we don't want to leak all the information, like all the people that are using Signal. True. What else? Yeah.
We don't want to be very contact.
More generally, you don't want to leak your address book to Signal. Right? So if you think about all the other messaging apps, the very first thing that they do is they upload your address book to then spam all of your friends to please install this nice fancy messaging app. And then these companies can build interesting bubbles of who is communicating with whom, what addresses you have, and so on. So ideally, we want to protect our address book from Signal, from Whisper systems, right? So the key idea here is we want to protect from Signal itself or from Whisper systems. We do not want to leak any information to Signal about who our contacts are, especially those that are not using Signal, right? Signal or Whisper system may know about the people that are using Signal, and it needs to protect this list of people against everybody else. But also, like, I only want to know who of my friends are using Signal, but not send all my list of friends to Signal. So how can we do this? Yeah? So you would hash all the phone numbers, and then like I would go through my contact list, go through one hash, and then query Signal and say, is this hash in your database? But that way they would already learn all my contacts, right? They would definitely learn all the ones that they have, right? Because they have the phone number and the hash. And they could just store the hashes that they don't have in their database yet. And as soon as somebody signs up, they have a match, right? Yeah, but I still, Whisper system would still learn how many contacts you have and the hashes of your contacts. Maybe it's already too much, right? Also, phone numbers are not that long. So I could just try all the phone numbers and then pre-compute all the hashes. Right? There's not that many. But good idea, right? This could work. Another idea would be access control, right? As a simple form. But obviously this doesn't work either. Same problem. The hardware security module is not in place. We are working with, like, we have to trust, we don't want to trust Signal, we don't want to trust Whisper systems, right? So we have to create some form of trust by not trusting Whisper systems. Can we solve this with crypto? Right? We could just encode all our contacts, send it to Whisper systems, and then decode it. Again, right, it doesn't work. Same as access control. Crypto like this doesn't work because Whisper system would again learn all the context. Yes, please. How do you know that the code that they are running is the code that you're looking at? Right, so that's another issue. But we'll need attestation for that. We'll get to that in a couple of slides. So what we would need is like some form of better cryptography. And obviously cryptographers got busy and already implemented that. And let's say we have the set of our contacts. We've got the set of contacts that use signal, and then we would do private set intersection. It's a nice cryptographic primitive that's horribly slow and scales to a couple of thousand entries. There's more than a couple of thousand signal users. So private set intersection does not scale to the size that signal has, right? But it offers, for smaller use cases, it offers a way where two parties jointly compute the intersection of their private input sets. Right? Both sides keep their set private. Both sides keep their information private. They run a protocol, private set intersection, and at the end of the protocol, both of them know which sets interact, right? Which entries overlap between the two sets. Now, this would be nice. This would be very cool if you could do that for Signal. It doesn't scale. So what Signal uses, it uses SGX. So the idea is somewhere in the cloud, they run a couple of servers that have in their private database the set of all Signal users. The enclave sends the private key to the Signal app. The Signal app encrypts the contacts with this private key, sends it over. We can do a regular set intersection, right, which is very, very simple. Like you check the two sets, you check for overlaps, and then you send the overlap back through this channel. Very cool, right? So this is a use case for Intel SGX. Is there an issue that you still see here?
How do we know that they're running SGX?
Exactly. How do we know if they are actually running SGX or not? How does the phone know the enclave runs the right program, right? Which goes back to your question to some extent. Well, the solution is the enclave itself is open source and fully open source. And the user, the phone, can compute and check the hash used in the attestation. So we slightly modify this protocol and make it just a little bit more complex, right? So the phone sends a challenge to the enclave running in the SGX compartment. The enclave sends back the private key and the attestation. If the attestation is correct, we encrypt the contact, send it over, and then send it back. Very good, right? So that way we can actually do this private set intersection with trusted hardware. Whom do we still trust in this setup? Yeah? We still trust Intel, correct? Whom do we also still trust? TSMC, yes. Whom else do we still trust? Qualcomm. On the phone? We still trust Qualcomm, again, TSMC. We still trust, let's say it's an Android phone, right? We still trust Google. We still trust Samsung or whatever is creating the app. And we also trust, to some extent, Whisper systems. Because did you verify the app that you installed from the Play Store? Right? So it's there's some layers of trust, but essentially you would trust Google that it serves the same app to everybody, And then if somebody would replace this app, this would be difficult or would be detected by somebody reverse engineering the app. So reducing your trust or not requiring as much trust into Whisper system as before. And Whisper system did as much as they could to get rid of any kind of, to make this as untrusted as possible from their end. The only additional step would be the full open source implementation of the Signal client. So far so good, right? Now, this SGX enclave also needs to store the information that it has, right? Like the SGX app, the enclave needs to store this information somewhere on disk. For example, if the server needs to be rebooted or whatnot. And for that, the system will encrypt the set of all the phone numbers and accounts using the sealing key, store this on disk, and then when the system is being rebooted, when the enclave is being reconstructed, it checks for the seal that, hey, the system, the enclave has not been tampered with, the enclave code is as we expect, and only then would it load the data correctly. So far so good. Now this is one example of using Intel SGX. We're going to walk a bit more quickly through another example, namely iPhone backups. And here the problem is that we want users to be able to back up their data to the cloud, but the user should be the only one who's able to recover the data. So we've got the phone, we do some backup to cloud storage, and then like if the user loses their phone, destroys it or whatnot, we want to recover the data somewhere else. On a new phone, or if the phone is flushed on the same phone again. So whom do we protect against? Other users, the cloud provider, and Apple, for example, and different kind of external parties, such as lawful interception with a subpoena or something. Interestingly, also adversaries have a lot of potential computing power. Now, the goal, again, offer cloud backups for data, but guarantee that users retain exclusive access. Now, Apple and the cloud are in our threat model because of legal interception, and access control itself is obviously not sufficient. What we could do is we could do some form of cryptography, right? On the phone itself, we trust the phone, we create a key, we then upload the data encrypted with the key to the cloud, and then make sure that this actually works. To get the data back onto our phones, we need the key. And now we are running a bit into a problem here, right? Like if you don't have the key, you cannot decrypt the data. But what do we do with the key, right? Where do we keep the key to recover it? And if the we cannot rely on what you have, right? We cannot store the key on the phone itself because you may lose the phone. We cannot just use a password because the adversary with the computational power could just guess the passwords. So this doesn't work either, and this kind of makes it challenging for us to provide this right setup where we have a strong cryptographic key without any trusted hardware on our end. So we need to have a way to back up the key, right? So what you can do is you can use an HSM, like an HSM to store the actual key. So the private key of the HSM can be hard-coded into the device. The device creates a random symmetric key, encrypts the phone data using the key that has been created on the phone, sends the data, the encrypted data, to the cloud storage, and then encrypts the key using the private key of the HSM and sends this to the HSM, and the HSM keeps secret this trusted this trusted key. All right, so there's a massive simplification of the protocol and whatnot. You can read the full blog post for more details. Now what we do is here, right, so the solution works as follows. We log in, we send the passcode and the private key, encrypted with the private key of the HSM to the iCloud server. Apple forwards this, checks if the passcode is correct on the HSM. So the HSM essentially runs the code, check passcode of user. If correct, return K. Otherwise, increment the count of tries. If the number of tries exceeds whatever you checked for, like the maximum you set, it destroys the key on the HSM, and the data is forever lost. Right? So that way you can pretty much query the key by only using your passcode, and that way you can protect the key against brute force attacks through passcodes. An adversary would be able to guess all the passcode entries really, really quickly, but not by going through an HSM. So you've added trusted hardware into the loop to recover a strong cryptographic key through a very weak passcode that you add. In this example, like, there's a simplification here. Apple could steal the key. That's why we need to add a little detail here. We create a private key on the phone, and then the server just returns it through encrypted with the private key. Right, it's just a small extension to this protocol. Now, Apple's HSMs run custom software. This software can be updated and should be updated. The Apple engineers need specific access keys to get to the hardware, require smart cards to update. Those are stored in sealed and tamper-evident bags. While not used, this gives them at least a way to detect when they are being used, and protects against kind of lawful interception, or at least makes it obvious that something has been done. Still need to trust Apple to install secure software in the first place. Right? So we still have Apple in the root of trust. Another form of trusted hardware is smart cards. And we're going to cover like some aspects of smart cards. You have a bunch of smart cards in your wallet, your health insurance card, your bank card, even your COM402, right? They're all smart cards, offering. Some of them offer contactless. Some of them offer with contact. These are the pins that you see here to carry out certain interactions. It's a plastic card with an integrated circuit, with an integrated chip that can process data that is often tamper resistant. So as soon as you try opening up, ripping the chip out and taking it apart, it will self-destruct. There's different types, memory cards, microprocessor cards that contain keys, certificates, whatnot, and other information. Some smart cards, such as a SIM, used in the phones, even contain additional functionalities to carry out the routing, encryption, and whatnot. Key certificates can be used for authentication, signatures, key management, and whatnot. One particular use case that we'll walk through is offline payments. And here the idea is that you would like to pay for something without the payment terminal actually being online. Right? Users should be able to signal to the bank to pay to a merchant without actually talking to the bank. So we've got the bank that issues us a card. We talk to the payment terminal, and then the payment terminal at one point in time tells the bank, hey, send money over to this other entity there, to the shop. And we may not want to, the payment terminal may not always be online or whatnot, right? And we are not online either. So There's a lot of actors in this protocol that are potentially malicious, right? Other users could be malicious. They could try to clone our card. The merchant could be malicious. They could try to overspend. The user could be malicious, trying to not pay, right? Different kind of external parties could be malicious, and so on. Adversaries may have a lot of computational power and time. And as money is involved, right, there's a very big incentive for them to actually carry out attacks, because that's like direct money. If you figure out an attack in this scenario, you get money, you get rich. People like to get rich, so this is a very common attack vector. Now, a simple protocol could be, right, giving this, or when you're interacting, when your card is interacting with the payment terminal, authenticate the card, verify the card holder, and then give a certificate of the transaction itself, such as I sign that I want to transfer 50 Swiss francs from here to there. Right? One option would be static data authentication. Right here, when the card is being created, we've got a signature of the bank that signs the card data and the certificate of the bank itself. Now, one of the issues that we face here is that the card itself can be copied easily. There's no freshness during the interaction, right? When we interact with the terminal, we send the card data signature, the PIN, the card terminal tells us the PIN is being entered, and the card just responds to the terminal, says PIN is okay. Now, the card terminal could take this transaction and replay it multiple times against the bank to spend money again and again. So there's no replay protection. The PIN verification similarly is unauthenticated. It accepts any card as long as the the card says PIN is okay. So I could try to read out a payment card of one of you folks, copy it, and then just have a modified card that whenever the card terminal asks, hey, is the PIN correct? It just says yes, right? And then if all the data is static, this allows me to spend some additional money. We can make this a bit more involved through dynamic authentication by going back and forth, where the card terminal sends a nonce, requiring the card to actually do some computation. One problem that solves the first problem, but one problem that remains is that the PIN verification is still unauthenticated. We could accept any card as long as the card has the alleged secret and can do the computation of the key on the card. Now, what we require is some form of online checking to verify that all of this information is actually valid. But it's an expensive process with a risk of money loss. So as you see here, when you're designing these kind of protocols, you need to be extremely careful about what the attacker model is, who the potential attackers are, and then figure out all the different steps in the process. Payment cards have existed, like digital payment cards have existed for around 35 years. And the protocols have gone through many different versions where researchers found attacks and attack vectors that have then been fixed, addressed, and modified to continuously make these interactions more secure. As we learn more about the possible attacks, figured out new ways of attacking, and then protecting against them. So that is another example of trusted hardware that has gotten more and more complex. I want to change gears a little bit and talk to you about side channels as well. We've now talked about trusted hardware, different kinds of trusted hardware. We've already looked at attack vectors. We've already looked at attacks. But now we're going to look at a particular attack. We're not going to look at attacking the system directly itself, but we're going to look at side channels. And a side channel essentially is an unintended leakage of information. Think of this as an information leak that an attacker can observe to slowly but surely extract more and more information, right? And side channel allow us to kind of infer something about the internal state. So let's say we want to do some very secure operation on the trusted hardware. Trusted hardware executes this very secure operation with secret information, and then the result of the very secure information is being restored, sent back to the user. Now everything that happens inside this blue box is supposed to be secret, and it's supposed to remain secret. But an attacker can kind of like try to infer some unintentional leakages from the hardware or software to learn the underlying secret. And well, we do have this trusted hardware here, but we are running an actual program on this trusted hardware. So an attacker may be able to observe time, like how long does it take to run the actual computation? How much power does it need? Right? Depending on the chip that we are using, depending on the trusted hardware that we are using, like if you're running a smart card, right? The power fluctuation may be massive depending on what kind of crypto operations we're doing. Electromagnetic emissions, right? So if I'm listening on a certain wire, I may be able to see certain fluctuations on the wire that are triggered through the computation or whatnot. Right? Let's start with the very classic side channel timing attack, and we're looking at RSA encryption. Like we generate large primes P and Q. We compute N equals P times Q. We compute the keys, choose the numbers. Accordingly, we create the public key, we create the private key, and we want to keep the private key secret, obviously. For encryption, we do the ciphertext. Ciphertext C is M to the power of E modulo N, and for decryption, we do C to the power of D modulo N. We do the decryption as follows. Now, let's say we go through decryption. Like this is just standard. That's why I went over it quickly. Right? If you do the decryption in a very simple form, and you've done the same in the exercises through a modular exponentiation operation, we would go through a square and multiply going through the individual bits in a simple for loop, checking if individual bits of D are 1. If so, we do a multiply mod n. Otherwise, we just copy, right? And we go over each bit of D. Now, as we're computing this, right, we know whether an iteration takes a long time depends on the case bit of the secret exponent. Right? So for each bit, like each time we go through the loop, we may be able to observe if it takes a long time or a short time. This assignment here, this is instantaneous. Right? This happens very, very quickly. It's just an assignment of a couple of bytes in memory. Whereas the computation up here is actually taking quite a while, right? Because we need to do a large int multiplication, and it will take quite a bit of time to run the operation. So iteration takes a long time, depends on the case bit of the secret exponent, as I mentioned. And the time depends on the number of ones overall. Right? So timing for the end-to-end computation depends on the number of ones, and if you have a fine enough observation of timing and power, we can actually analyze the individual steps due to the high cost of the multiplication. So a power analysis pretty much takes like a smart card, an oscilloscope, measuring power consumption that is then being fed into the computer, which controls the interaction with the smart card. And by observing the actual power traces, we can see that, hey, this is mapping to a 1-bit, this is mapping to a 0-bit. The data that we see here is still quite noisy, right? So we see that the quantized voltage goes up and down. It's still quite noisy, but we can map certain patterns and then map 0 bytes. Like the 1 bytes are coming with 2 peaks, the 0 bytes with 1, looking at how expensive the computation is overall. Right, so this allows us to map this computation into individual parts and then observe the 1s and the 0s. That's power analysis. So we are observing how much power the card actually draws. Right? Observing it by so you could protect against this by adding capacitors before the card, kind of like diluting and reducing the amount of side channel, but it's very hard to get rid of any power side channel. The easiest way to get rid of a power side channel is, what would be a way to get rid of the power side channel? Apart from a capacitor. Yeah. Have your own energy, yes. Have a battery, right? A simple battery will get rid of the power side channel. Because that way you can measure the battery before and you can measure the battery afterwards. But again, right, we see that the card is set up in a lab environment, right? So this would require us to have a battery inside the chip itself, in the tamper-resistant container, which may be quite hard to achieve. Electromagnetic emissions, right? That's another point. There's interactions that happen. There's like the electromagnetic noise that is being sent out through any kind of computation, and you can use the same electromagnetic emissions to infer the different secret computation. Countermeasures against side channels are, for example, hiding, lower the signal-to-noise ratio, for example, by generating noise, randomized execution order, like asynchronous logic styles, different kind of exchanges, modifications, whatnot. Masking, split state into different chairs, forces the adversary to recombine the different parts. Leakage resilience would be preventing leakage in the first place by updating the secret or whatnot. Right, so there's different angles on how to protect against side channels at the hardware level. So these are architectural side channels that we've looked at, such as power, electromagnetic resistance, but there's also other side channels. And especially since 2018, microarchitectural side channels have kind of revolutionized a lot of the attack research on trusted computing systems. Now, microarchitectural side channels leverage some microarchitectural leakage to recover information and then to allowing the attacker to learn secrets about some internal state of the hardware, such as between user space and the kernel, between different user space processes, or even between a user space process and a trusted SGX enclave in the most privileged form. We're going to talk about the two most well-known side channel attacks, Meltdown and Spectre, which kind of started this whole field of research that is actually still fairly active by looking at all different kinds of side channels. Meltdown is like a catastrophic attack which made it possible for any user space process to read all of kernel memory, including like the secret data in the kernel. It's just a side effect of how different microarchitectural features were implemented. And like by chance, the AMD x86 implementations were not affected. right? It's essentially a race condition between memory access and protection check. So it's when you access memory, there's some latency during the execution of an instruction, and then you do the protection check if you're allowed to access or not. So it exploits the microarchitectural nature of caches, that something is left in the cache that is not part of the architectural state, some internal kind of state of the cache itself. So the attacker executes a forbidden access, speculatively uses the result to obtain non-architectural side effects that then allows them to reveal the secret before the forbidden access is squashed. I'm going to go through an example here. As a quick background and a quick reminder from your operating system class, right? In modern operating system, we are using virtual memory. Virtual memory maps a certain amount of physical memory that we see at the bottom into virtual memory, where each process assumes that they have the full virtual address space. So 4 gigabytes or 256 terabytes of memory accessible. And the operating system actually manages the mapping between what the process sees and the actual physical memory that is available. So we have a certain amount of fixed physical memory pages that are mapped into user space processes and, for example, kernel memory. The idea here is that the operating systems map physical kernel pages into every user's virtual memory space, with the idea here that the kernel is being shared across all the different processes, thereby simplifying the workload to some extent. So if we have one virtual address space that consists both the user program and the kernel program, right, all the kernel data, this enables very fast context or faster context switching from user space to kernel space, because everything is mapped in one virtual address space. Now what we do have is we have two different protection levels. We are either running in user space or in kernel space. When you're running in kernel space, when you're running in user space, any access to the memory area that is marked as kernel memory would result in an exception, a trap, stopping the execution of the user space process, right? But everything is mapped in the same address space. Just accesses to the kernel pages from when you're running as a user context would result in a protection fault. Unfortunately, this check is or was done asynchronously. So what Meltdown actually does, like the steps for Meltdown, is the attacker executes a forbidden access, like you dereference wherever, which points somewhere into kernel memory. So obviously, this instruction will never finish. This instruction will never retire. So you will not be able to read this information. It will trap. Right? So the attacker, while executing in user space, tries to read a secret value from somewhere else in the address space, which in the kernel it was mapped in the virtual address space. The value will be removed from the reorder buffer, or ROB, and then an exception is thrown, right? Likely either stopping the process or calling the exception handler in the process that says, hey, you executed an illegal memory address. This is not good, right? So the instruction itself that would load the value from the kernel is stopped from executing, is stopped from retiring. But the instruction actually executes speculatively until the access level check completes and then throws the exception. And during that time window, a lot of the side effects can already be made visible. So the attacker executes this wherever, secret equals wherever, and then speculatively uses this secret. For example, doing some follow-up instructions that depend on the secret. Now, all of this computation will be undone, but we can use this to actually leave some non-architectural side effects, right? So before the exception is thrown, something else will be executed speculatively to follow up instructions. So what we can do is we can do array secret times 4096 and access that. Now what this does is it reveals the actual secret, right? Because we multiply secret times 4096. And if wherever we are loading 1 byte from memory, secret can be one of 256 values, which maps to one of 256 pages, which would then like overwrite the value in array. But all of this computation is undone. Like when the speculation fails, when the exception triggers, all of this computation is removed. But what has happened? Like what is left?
We access the array so one page will be probably left somewhere. Something will be cached.
We have flushed something out of the cache. Right? So the cache value, like something else was in the cache before. During the speculative execution, we kick this out of the cache. And now, when we access it, the access is fast here, the access is fast here, the access is fast here, the access is fast here. But here, the speculative execution kicked the element out of the cache, and the access will be slow. So we have a timing side channel that actually leaks this information. So this gives us a race or a timing condition that allows us to check which element has been evicted from the cache, and thereby we know what the original value of the secret was. Right? So make sure that a secret the attacker cannot read leaves a trace before it is cancelled. And then we can do a prime and probe cache attack to actually learn the secret. So this is combining this micro-architectural bug that leaves this trace with a prime and probe attack to figure out if this was actually true. Was this clear? So the trick is, right, we have all the memory of both the user space process and the kernel mapped in a single address space. So everything is in one address space. But in this address space, if you're executing in user space, if you're executing the application itself, all the data from the kernel are not accessible. If you would access it, this results in exception. So the trick that we are doing is we are accessing the data in the kernel, and then in this data during speculation, right, the CPU just continues to speculatively execute, assuming that the access will be benign. It speculatively executes the next couple of instructions to make sure that the CPU runs fast, right? And then in the speculative execution window, we do a couple of accesses, including like kicking this out from the cache. Okay? After this has been kicked out, at one point in time the exception triggers because the speculation failed. The CPU will undo all of the instructions it executed and then continue at the correct location after the exception. But interestingly, right, this is still in the cache, and we can then figure out which entry in the cache was actually evicted. Question?
So the attacker has to create a beforehand?
Yes, for example. The attacker creates this array beforehand, accesses all the locations, makes sure that all of the locations are in the cache, then accesses the secret location in the kernel, and which will fail. But in a modern instruction, if you remember from your architecture classes, there's usually like 40 instructions in flight, 60 instructions, 100, 200 instructions. Like the CPU executes many instructions not in parallel, but they are in the pipeline that are concurrently being executed. Like a small part of each instruction is being executed at the same time. And to do this check, if like the access check would slow things down. If you would do the access check first before loading the value, this would result in a massive slowdown. This is why this is done in parallel, because you just assume, oh, we can flush and we can undo the speculation if the speculation fails. Cool. Other questions? So interestingly, this did affect a lot of CPUs, like Intel x86. Most processors of the last 20, 30 years, 20 years when Meltdown was discovered, AMD x86 was not impacted, interestingly, because they were doing the access check before, and a whole bunch of other processors that are on there as well. Possible mitigations, right? The obvious solution is to change the processor design so that it's no longer vulnerable to this type of bug. Like do the privilege level check before the result of the speculation. AMD did this already by chance. And the other line of mitigation, like if you have hardware out there that is vulnerable to this, is to isolate user space in kernel. In Linux, kernel page table isolation kind of splits the page table so that before we had user space and kernel space in one virtual address space. The change was to split this into two, right? When we were executing in user space, there's only a tiny bit of the kernel mapped. Whenever you execute a system call, the rest of it is mapped. When you go back to user space, you unmap the rest of it. And this prohibits Meltdown at a fairly high performance overhead, because you constantly have to map, unmap different kind of page tables, which is a very expensive operation on modern architectures. That's one side channel, one microarchitectural side channel, Meltdown. I promised you another one, which is Spectre. Spectre is another one that allowed reading all memory and addresses another shared resource, namely branch predictors. Right? So for simplicity, branch predictors are not unique per thread, but shared among SMT threads, simultaneous multi-threading. So on your system, right, if you have 4 cores, like maybe your laptop has 4 cores, each of these cores has 2 threads, and the threads leverage the same underlying resources. For example, the same set of branch predictors, the same set of functional units, and so on. For the different processing. This is a way to increase the utilization of the different units on the system. And Spectre exploits side effects of mispredicted speculative execution. Again, we're leveraging speculative execution here, but here we're leveraging the misprediction of the speculative execution, not the lack of the privilege check that comes later during the execution. Misspeculation does not affect the architectural state, same as before, but it may affect the microarchitectural state where some traces may be left that we can then tease out. So the idea here is to get the victim to speculatively execute leaky code whose non-architectural side effects then reveal the secret. So we execute some leaky code here. With an appropriate value for x, we can read anything we want, right? So we are leveraging, like again, an x that is being pushed into the information. And then speculatively execute if x is smaller than array 1 size, right? So if the program is executing, the program assumes, like the CPU assumes over the many executions, that the last 10 times I executed this loop, this was true. Therefore, the CPU remembers that, hey, this loop has always been, the if branch has always been executed, so it will speculatively execute the leaky instruction, even if x is outside of the array size. Right? Now, an attacker will prime the cache by executing it normally, and then modify x, so that it's outside of the array size, reading arbitrary memory, to then, during a misprediction, access arbitrary memory speculatively, which will then be undone by the CPU, but the microarchitectural effects remain. So if we expand this a bit, again we have an array 2 so it's like a double indirect access, where array 2 again serves the same purpose of what we did before in the meltdown attack with as a leakage gadget. So we speculatively loaded the value. The trace will be left in the cache because the value has again been kicked out of this access. So we force the victim to misspeculate in steps 1 and 2, and then perform a prime and probe cache attack to again learn the secret, to uncover the secret information on the side here. Very simple example, very simple attack that wasn't detected that was missed in architectures for around 30 plus years. So this has been in all the hardware for 30 plus years, all the CPUs that have been created since then, because people assumed that the microarchitectural state does not leak any information. And then security people looked at it, security researchers analyzed this and discovered that, hey, there's a kind of massive amount of leakage that is actually happening. Possible mitigations, right? You can disable speculative execution and reduce the speed of your CPU to about 2% of the original speed. So not very recommended. You can separate branch predictors per process or thread, right? That's the current solution that is usually being done. Like if you look at OpenBSD, in 2018, when the first speculative side channels came out, they just disabled SMT, simultaneous multi-threading. And looking back, this was likely the best decision they ever made. Right? Just disable the use of these shared resources. You can do some software approaches, like run only one application per processor, like in scheduling, so this reduces this attack window too quite a bit. You can do partial and application-specific software approaches and do different kind of mitigations and whatnot, but it's kind of hard, right? It's very hard to fix all the different angles. Spectre is not easy to fix. It will haunt us for quite some time. That's a quote on the web page. Now, if you run any kind of modern system, like if you run in Linux, you can check your system for different mitigations that are in place, right? For in sys devices system CPU vulnerabilities, you can just cat and then check what your system is affected on and what kind of mitigations the operating system kernel has to run to limit the effects of the attacks. Now, this comes at a performance price, right? So this comes at 20–30% performance of your CPU. Running these mitigations after the fact, because the hardware itself was not designed to actually mitigate these effects. Now, luckily, we have what is called microcode update, so you can change the code that your CPU runs to execute the instructions, including like fairly heavyweight changes to the underlying system, but it comes at quite a massive price, right? So Intel will release microcode updates to the different systems, to their different CPU families, to mitigate all kinds of microarchitectural side channels or other bugs that they have, right? So they update the software that is running on your CPU. Like your CPU just has like a piece of firmware running on it that needs to be updated regularly to fix bugs, because CPUs are so complex now that they require updates. Intel learned this in the 90s when they had a very... Does anybody know when Intel learned this and when Intel introduced microcode? The FO diff bug, yeah. It's a famous bug on Intel hardware. If you executed a floating point division with the right parameters, you just crash the system. You hard reset the CPU. which is a fairly severe vulnerability if you consider it if you consider running a JavaScript program that may do a division, right? And back in the day, Intel didn't have microcode, and this resulted in a very expensive lawsuit for them. Now, interestingly, they were lucky that they had microcode in place, allowing them to update and patch certain behavior here. Even with trusted hardware, vendors require some trust, right? Like if you go back to the backup data system from Apple, as we discussed, the HSM manufacturer needs to be trusted, Apple needs to be trusted to install the correct code and so on. For Signal, we need to trust Intel and Signal, as we discussed. And yeah, there's layers of trust that need to be added on top of each other. We've gone through several iterations of trusted hardware. Trusted hardware exists. It comes at a price. And it offers different kind of the three key properties of isolation, attestation, and sealing. Having trusted hardware alone doesn't mean you don't need to think about the protocols, and you need to enforce and design secure protocols, as we've seen with the smart cards. And building trusted hardware is extremely difficult. See, for example, the side channels, both power and microarchitectural ones that we looked at. Trusted hardware still means that you need to trust the manufacturer, but at least there's a separation of privilege that we can look at. So some takeaways, right? Trusted hardware is useful in certain scenarios. We've discussed some of the use cases. We have learned how trusted hardware works, what guarantees it provides, different kind of case studies, and we looked into side channel attacks to make this a bit more concrete. That's all that I have for today. Thank you very much. I'll see you next week, and I will remain around for questions if you have any.